This problem covers concepts 5, 6, and 7, internal fluid flow with friction loss, pump analysis, as well as flow through porous media. So our problem definition involves a pump pumping through a segment of pipe and a fluidized bed. We have givens for the physical situation, which are here for all the different properties of the system. And we're tasked with finding the pump head requirement for a flow rate, and then also finding the flow rate that would make this system have turbulent flow, and then from that turbulent flow, the resulting pump head requirement. We can make some assumptions, so we can use the equations that we use. We're going to assume no change in gravity. The gravity is this given quantity. The system is at atmospheric pressure. There is negligible height change, and that the water is at 20 degrees C, and atmospheric pressure from table A9, we have these properties of water in that context. So here we'll analyze the system from point 1 to 2, and we'll use the Bernoulli equation between those 2 points in order to derive an equation for pump head, part of our fulfilling the requirement for pump analysis. And we can simplify that down using our assumptions. And then because we have, due to the fact that the feed pipe dimensions are identical to the outlet of the porous media, we can use continuity to simplify it further, that the pump head is going to be equivalent to the head loss over the system. And then we can see that the head loss here is going to be equivalent to the friction loss over gravity. So looking at internal fluid flow with friction loss, we're going to be initially, based on the Reynolds number, looking at the laminar portion of that requirement. So when we evaluate that, we find that the Reynolds number for our flow is 9.89, which is less than the requirement for flow through porous media or for other types of fluid flow. So therefore, we can utilize this form of the friction factor, and we can find the friction loss equivalent to this equation for the internal fluid flow for the pipe, because we know that the friction loss over the system is going to be the sum of the friction loss through the pipe and the fluidized bed. Following, we utilize the laminar portion of the air gun equation for our flow through porous media requirement, laminar-wise. And then we combine our terms to find an equation for head, and we find that the pump head is equivalent to about 2.86 centimeters. It's a pretty small pump. So then, for the turbulent discussion of internal fluid flow and flow through porous media, we need to find the fluid flow rate that would make the flow in the system turbulent. So we know for flow through porous media, it's going to be turbulent when the Reynolds number is above 20,000. We can rearrange the equations that we have for the flow rate and find that the flow rate would need to be about 1.58 liters per second in that situation. And then we need to find the new pump head requirement for this turbulent flow regime. We utilize different definitions for the friction factor in the air gun equation due to the turbulent conditions, which again fulfills the turbulent requirement for internal fluid flow and flow through porous media. And we come out with this combined equation for pump head. So we find here that pump head is going to be equivalent to 258.9 meters, which is a much bigger pump, sort of shows the level that this second part of the problem is realistic. This problem is going to cover concepts 8 and 9, so that is external fluid flow, drag, and compressible flow. So we've got a potato firing upwards from a potato gun, and we're tasked to find the initial velocity and the Mach number of the potato at that initial velocity. We can take our all of our known properties from this problem description. We can make some assumptions that the potato is a smooth, perfect sphere, that the gravity is equal to a common assumption, that the air is at 20 degrees C, so we know from table A15 some basic properties of air. And for the B, we're going to assume air is an ideal gas in order to find that Mach number. So we're going to construct a momentum balance first, define our terms, and then come up with this expression for the drag force in order to solve for something that will give us that initial velocity. We are going to have our coefficient of drag here be 0.44 for the smooth sphere in turbulent fluid air. We're going to combine terms and rearrange for dv dt, so we can do some rearranging and integration in order to finally find a relationship with velocity in terms of time. And I personally used the Excel solver tool to find that initial velocity that satisfied the the physical context at t equals 5 seconds. And then we can also verify that turbulent assumption using this formula for the Reynolds number, which we've done here. And then from there, we find that the initial velocity is this quantity, so the potato gun performs better than designed. Okay, finally, in order to address compressible flow, we need to calculate the Mach number, so we need to find c, the local speed of sound, which is equivalent to k times r times t. And we defined these properties here, and we had k from a handout that defines Cp over Cv up here. And then we move through this, combine terms, we find the Mach number is equal to the velocity over the local speed of sound, and then we can find that our initial Mach number is this value here, pretty low, so it's not very close to the speed of sound. Okay, so this problem is going to cover concepts 10, 11, and a portion of concept 12. So we're going to be looking at microscopic mass and momentum balances using Navier-Stokes, boundary conditions, and an analytical solution to Navier-Stokes. Here we have the situation, we've got rainwater during a rainstorm flowing off a roof into a gutter pipe running vertically. We want to find the analytical solution to the system. And we have the distance here across the pipe, the full diameter. We're going to make some assumptions to use Navier-Stokes based on the physical situation so that it's steady state, flow is incompressible, the flow is fully developed, the flow is gravity driven, there's a negligible pressure gradient, that there is no swirling flow. So there's no flow in the radial or angular directions. We're going to utilize continuity. So I've retyped this from our handouts, and then we're going to make some assumptions in order to eliminate terms. So this first term is going to go to 0 because it's steady state, so nothing is going to vary in time. The second term is going to go to 0 because there's no swirling flow, so there's no radial velocity. This third term is going to go to 0 because, for the same reason, there's no angular velocity, no swirling flow. And this final term is going to go to 0 because it's fully developed, so the flow does not vary with z. Therefore, continuity is satisfied. Moving on, we're going to do a momentum balance using Navier-Stokes for the z component using cylindrical coordinates. So again, this equation is from one of our handouts on the equations of motion. And we're going to do a similar thing where we eliminate terms based on the assumption. This first term is going to go to 0. It's steady state. Nothing varies with time. Second term and third term are going to go to 0 because there is no radial or angular velocity, because there's no swirling flow. And then this final term is going to 0 because it's fully developed. So there's no velocity variance with the z direction. Then we see this term here go to 0 because it's a gravity-driven flow. There's no pressure gradient, a negligible pressure gradient at least. This term will remain. This term is going to go to 0 because of our swirling flow assumption. So there's no theta variance. And then this term is going to go to 0 because it's fully developed. There's no variance with the z direction. Therefore, we get this, which we can rearrange and integrate until we find a equation for that velocity in the z direction as it varies with radius. We have two boundary conditions. We're going to say it's symmetric flow. So at the center line, the derivative of the z direction velocity with respect to r is going to be 0. It's going to have a flow profile where there's a sort of a flat middle portion if you look at the derivative. Then there's going to be no slip at the wall, so the velocity is going to be 0 at plus or minus half the diameter. We can utilize those boundary conditions, so we can find the coefficients that satisfy our boundary conditions. We find that that first coefficient is 0, and that the second coefficient is equivalent to this. And then analytically, we have our derivation, our equation for the velocity in the z direction with respect to the radius. This problem covers phenomenon 12, numerical solutions to Navier-Stokes. We are given a relationship equation for the second derivative of velocity with respect to x, some other knowns, and we are tasked with finding the velocity at the center line without using an equation. We assume it's steady state and compressible and the flow is fully developed, and we assume that it is water at 20 degrees C, so we have these properties from table A9. I have this rearranged equation for velocity in terms of that second derivative. some delta x, and then the previous and following velocities at plus or minus that delta x. We define all that and use Excel. We can also compare it to a known analytical solution to see how close we get, and we find the velocity here at the center line, and we see that it's pretty similar to the analytical solution.